In philosophy, systems theory, science, and art, emergence is a process whereby larger entities, patterns, and regularities arise through interactions among smaller or simpler entities that themselves do not exhibit such properties. Emergence is central in theories of integrative levels and of complex systems. For instance, the phenomenon life as studied in biology is commonly perceived as an emergent property of interacting molecules as studied in chemistry, whose phenomena reflect interactions among elementary particles, modeled in particle physics, that at such higher mass, via substantial conglomeration, exhibit motion as modeled in gravitational physics. Neurobiological phenomena are often presumed to suffice as the underlying basis of psychological phenomena, whereby economic phenomena are in turn presumed to principally emerge. In philosophy, emergence typically refers to emergentism. Almost all accounts of emergentism include a form of epistemic or ontological irreducibility to the lower levels. In philosophy, emergence is often understood to be a claim about the etiology of a system's properties. An emergent property of a system, in this context, is one that is not a property of any component of that system, but is still a feature of the system as a whole. Nikolai Hartmann, one of the first modern philosophers to write on emergence, termed this categorial novum. Definitions. This idea of emergence has been around since at least the time of Aristotle. John Stuart Mill and Julian Huxley are two of many scientists and philosophers who have written on the concept. The term emergent was coined by philosopher G. H. Lewis, who wrote, "Every resultant is either a sum or a difference of the cooperant forces, the sum, when the directions are the same, the difference, when the directions are contrary." Further, every resultant is clearly traceable in its components, because these are homogeneous and commensurable. It is otherwise with emergence, when, instead of adding measurable motion to measurable motion, or things of one kind to other individuals of their kind, there is a cooperation of things of unlike kinds. The emergent is unlike its components insofar as these are incommensurable, and it cannot be reduced to their sum or their difference. Economist Jeffrey Goldstein provided a current definition of emergence in the journal Emergence. Goldstein initially defined emergence as the arising of novel and coherent structures, patterns and properties during the process of self-organization in complex systems. Goldstein's definition can be further elaborated to describe the qualities of this definition in more detail. The common characteristics are radical novelty, coherence or correlation, a global or macro level, it is the product of a dynamical process, and it is ostensive, for good measure. Goldstein throws in supervenience. Systems scientist Peter Corning also says that living systems cannot be reduced to underlying laws of physics. Rules, or laws, have no causal efficacy, they do not in fact generate anything. They serve merely to describe regularities and consistent relationships in nature. These patterns may be very illuminating and important, but the underlying causal agencies must be separately specified. But that aside, the game of chess illustrates why any laws or rules of emergence and evolution are insufficient. Even in a chess game, you cannot use the rules to predict history, i.e., the course of any given game. Indeed, you cannot even reliably predict the next move in a chess game. Why? Because the system involves more than the rules of the game. It also includes the players and their unfolding, moment-by-moment decisions among a very large number of available options at each choice point. The game of chess is inescapably historical, even though it is also constrained and shaped by a set of rules, not to mention the laws of physics. Moreover, and this is a key point, the game of chess is also shaped by teleonomic, cybernetic, feedback-driven influences. It is not simply a self-ordered process, it involves an organized, purposeful activity. Strong and weak emergence. Usage of the notion emergence may generally be subdivided into two perspectives, that of weak emergence and strong emergence. In terms of physical systems, weak emergence is a type of emergence in which the emergent property is amenable to computer simulation. This is opposed to the older notion of strong emergence, in which the emergent property cannot be simulated by a computer. Some common points between the two notions are that emergence concerns new properties produced as the system grows, which is to say ones which are not shared with its components or prior states. Also, it is assumed that the properties are supervenient rather than metaphysically primitive. Weak emergence describes new properties arising in systems as a result of the interactions at an elemental level. However, it is stipulated that the properties can be determined by observing or simulating the system, and not by any process of a priori analysis. The DAW notes that weak emergence is not a universal metaphysical solvent, as weak emergence leads to the conclusion that matter itself contains elements of awareness to it. However, the DAW concludes that adopting this view would provide a precise notion that emergence is involved in consciousness, and second, the notion of weak emergence is metaphysically benign. Strong emergence describes the direct causal action of a high-level system upon its components. Qualities produced this way are irreducible to the system's constituent parts. The whole is other than the sum of its parts. An example from physics of such emergence is water, being seemingly unpredictable even after an exhaustive study of the properties of its constituent atoms of hydrogen and oxygen. It follows then that no simulation of the system can exist, for such a simulation would itself constitute a reduction of the system to its constituent parts. However, the debate about whether or not the whole can be predicted from the properties of the parts misses the point. Wholes produce unique combined effects, but many of these effects may be co-determined by the context and the interactions between the whole and its environment. In accordance with his synergism hypothesis, Corning-Hall also stated, "It is the synergistic effects produced by wholes that are the very cause of the evolution of complexity in nature." Novelist Arthur Koestler used the metaphor of Janus to illustrate how the two perspectives should be treated as non-exclusive, and should work together to address the issues of emergence. Further, the ability to reduce everything to simple fundamental laws does not imply the ability to start from those laws and reconstruct the universe. The constructionist hypothesis breaks down when confronted with the twin difficulties of scale and complexity. At each level of complexity, entirely new properties appear. Psychology is not applied biology, nor is biology applied chemistry. We can now see that the whole becomes not merely more, but very different from the sum of its parts. The plausibility of strong emergence is questioned by some as contravening our usual understanding of physics. Mark A. Bador observes, although strong emergence is logically possible, it is uncomfortably like magic. How does an irreducible but supervenient downward causal power arise? Since by definition it cannot be due to the aggregation of the micro-level potentialities, such causal powers would be quite unlike anything within our scientific ken. This not only indicates how they will discomfort reasonable forms of materialism, their mysteriousness will only heighten the traditional worry that emergence entails illegitimately getting something from nothing. Meanwhile, others have worked towards developing analytical evidence of strong emergence. In 2009, Gu al. presented a class of physical systems that exhibits non-computable macroscopic properties. More precisely, if one could compute certain macroscopic properties of these systems from the microscopic description of these systems, then one would be able to solve computational problems known to be undecidable in computer science. They concluded that although macroscopic concepts are essential for understanding our world, much of fundamental physics has been devoted to the search for a "theory of everything," a set of equations that perfectly describe the behavior of all fundamental particles. The view that this is the goal of science rests in part on the rationale that such a theory would allow us to derive the behavior of all macroscopic concepts, at least in principle. The evidence we have presented suggests that this view may be overly optimistic. A "theory of everything" is one of many components necessary for complete understanding of the universe, but is not necessarily the only one. The development of macroscopic laws from first principles may involve more than just systematic logic, and could require conjectures suggested by experiments, simulations or insight. Emergent structures are patterns that emerge via collective actions of many individual entities. To explain such patterns, one might conclude, per Aristotle, that emergent structures are other than the sum of their parts on the assumption that the emergent order will not arise if the various parts simply interact independently of one another. However, there are those who disagree. According to this argument, the interaction of each part with its immediate surroundings causes a complex chain of processes that can lead to order in some form. In fact, some systems in nature are observed to exhibit emergence based upon the interactions of autonomous parts, and some others exhibit emergence that at least at present cannot be reduced in this way. Objective or subjective quality. The properties of complexity and organization of any system are considered by Crutchfield to be subjective qualities, determined by the observer. Defining structure and detecting the emergence of complexity in nature are inherently subjective, though essential, scientific activities. Despite the difficulties, these problems can be analyzed in terms of how model-building observers infer from measurements the computational capabilities embedded in nonlinear processes. An observer's notion of what is ordered, what is random, and what is complex in its environment depends directly on its computational resources, the amount of raw measurement data, of memory, and of time available for estimation and inference. The discovery of structure in an environment depends more critically and subtly, though, on how those resources are organized. The descriptive power of the observer's chosen computational model class, for example, can be an overwhelming determinant in finding regularity in data. On the other hand, Peter Corning argues, must the synergies be perceived, observed in order to qualify as emergent effects, as some theorists claim? Most emphatically not. The synergies associated with emergence are real and measurable, even if nobody is there to observe them. In religion, art and humanities. In religion, emergence grounds expressions of religious naturalism and syntheism in which a sense of the sacred is perceived in the workings of entirely naturalistic processes by which more complex forms arise or evolve from simpler forms. Examples are detailed in The Sacred Emergence of Nature by Ursula Goodenough and Terence Deacon and Beyond Reductionism, Reinventing the Sacred by Stuart Kaufman, both from 2006, and in Syntheism, Creating God in the Internet Age by Alexander Bard and Jan Soderquist from 2014. An early argument for the emergence of social formations, in part stemming from religion, can be found in Max Weber's most famous work, The Protestant Ethic and the Spirit of Capitalism in Art. Emergence is used to explore the origins of novelty, creativity, and authorship. Some art literary theorists. The concept of emergence has also been applied to the theory of literature and art, history, linguistics, cognitive sciences, etc., by the teachings of Jean-Marie Gracine at the University of Limoges. In international development, concepts of emergence have been used within a theory of social change termed seed scale to show how standard principles interact to bring forward socio-economic development fitted to cultural values, community economics, and natural environment. These principles can be implemented utilizing a sequence of standardized tasks that self-assemble in individually specific ways utilizing recursive, evaluative criteria. In post-colonial studies, the term emerging literature refers to a contemporary body of texts that is gaining momentum in the global literary landscape. By opposition, emergent literature is rather a concept used in the theory of literature.